In the next lecture, we will be proving the Krull-Schmidt theorem, which says that the decomposition of a module that satisfies the ascending chain condition and the descending chain condition into indecomposables, into a sum of indecomposables, is essentially unique. In that proof, there's a certain technical lemma that's required, and that basically involves understanding the endomorphism ring of an indecomposable module. And that's what I'm going to do in this lecture. So we're going to study the endomorphism ring of an indecomposable module. So if R is a ring, M an R module, we've seen that we can think of this end Rm, which is nothing but the R module homomorphisms from M to M, which we can think of as the arrows from M to M in the category of R modules. And this is in fact a ring because we can add two homomorphisms pointwise, and we can also compose them, giving rise to an associative product on this ring. Okay, so for example, simplest example, well, maybe not simplest, but the most a very interesting example is that if you take any ring R and you look at R itself as a left R module, then this is isomorphic to phi A, which is this is the same actually as, so the endomorphisms are given by phi A, which takes R to R times A for every A in R. So you can check that phi A is an R module endomorphism, and conversely, given any R module endomorphism of R, the moment you know where it takes 1, it will take 1 to some element A, you can show that's actually equal to phi A. And here we have phi A composed with phi B of R. Well, that turns out to be phi B of R multiplied by A, but phi B of R is R times B, so this is R times B times A, but that's R BA by associativity, and that's just phi of BAR. So end RR is not exactly R, it is the ring opposite to R, where the order of multiplication is reversed. Okay, so now we'll be interested in the endomorphism ring of an indecomposable R module, and the property that we will be interested in is the fact that it is what is called a local ring. So for our purposes, we will take the following as the definition of a local ring. I'm sure most of you are familiar with, well, some of you at least are familiar with the notion of a local ring for a commutative ring. Maybe you're not all familiar with a local ring which is non-commutative. But we'll just give a very simple definition. A ring R, and this will be applying not to the original ring R whose module we're looking at, but to its endomorphism ring. But this definition is general. A ring R is called a local ring if its set M of non-units, that means elements which don't have an inverse, is a two-sided ideal. Okay, what is the meaning of an ideal? You can recall from Algebra-I. I is called an ideal if, firstly, I is a subgroup of the additive group. Then secondly, it's closed under left and right multiplication by arbitrary elements of R. So if A belongs to I, R belongs to R, then that implies that AR belongs to I and RA belongs to I. Okay, and that's it. So these are the two conditions. And sometimes we would ask for a left ideal which only satisfies the second condition, or a right ideal which only satisfies this first condition. But here we are looking at two-sided ideals. Okay, so let's just look at some examples to fix this notion. Z mod p to the kz is local. The non-units are precisely the elements which are multiples of p, and so they form an ideal here. Z is not local, and matrices, let's just stick to fields for now. Is this local or not? Well, you can show that if you take any non-zero element of any non-zero matrix, then the two-sided ideal that the smallest two-sided ideal that contains it is the entire matrix ring. So there are lots of non-units in M and K, that is matrices with which are not of full rank, but they do not unfortunately form an ideal. So this is not local. And now for the main theorem of this lecture. The theorem is let M be an indecomposable R module satisfying the ACC and the DCC. Then end Rm is a local ring. So before proving this, we will prove a certain lemma, and this lemma is due to a mathematician called Fitting, and it says that if M is as above, or maybe we just need if M satisfies the DCC, in fact. Well, let's just keep it M is as above, and G belongs to end Rm, then either G is a unit or G is nilpotent. Okay, recall that nilpotent means that G to the n is equal to 0 for some n belonging to n. Some power of G vanishes. Okay, so let's prove Fitting's lemma. And so what you do is you take any G in end Rm, and you consider M. Well, it contains as a submodule the image of G under M, which in turn contains G squared M, and so on. Now, because of the descending chain condition, there is some stage after which this sequence stabilizes. So by the DCC, G to the nm is equal to G to the n plus Im for all I greater than or equal to 0 for some natural number n in n. And what this means is that in particular G to the nm is equal to g to the power 2nm. Or in other words, g to the power n is an isomorphism from g to the power nm to g to the power 2nm. Okay, so now let's proceed further. So if x is in M, then there exists y in M such that g to the power nx is g to the power 2ny, right? Just because g to the power nm is g to the power 2nm. And so I can write x as g to the power ny plus x minus g to the power ny. Now let's look at these two parts of the sum. This belongs to the image of g to the power n, and this, well, if I apply g to the power n to this, so I take g to the power nx minus g to the power ny, then I'll get g to the power nx minus g to the power 2ny, which is 0 because g to the power 2ny is equal to g to the power nx. So this belongs to the kernel of g to the power n. So I've written x as a sum of two things, one in the image of g to the power n and the other in the kernel of g to the power n. Moreover, g to the power n, when restricted to g to the power nm, is an isomorphism, and therefore it has no kernel in g to the power nm. So also we have that g to the power image of g to the power m intersection with the kernel of g to the power n is 0. So what we get is a direct sum decomposition of m. Okay, so but m is indecomposable, so there are only two possibilities. One of these summands is the whole thing. So either m is the image of g to the power n, or m is the kernel of g to the power n. Now m is the kernel of g to the power n means that g is nilpotent. And that was one of the options in Fitting's lemma, in Fitting's dichotomy, so to speak. And so we just need to check that if m is the image of g to the power n, then g is in fact an isomorphism or a unit in end Rm. So let's just look at that. So if image of g to the power n is equal to m for some n, then what we have is that g is surjective. Therefore, what we have is that g, if you take from m mod kernel of g to m, is an isomorphism. But that means that the length of m mod kernel of g, remember m satisfies both the ascending chain condition and the descending chain condition, and therefore it is a finite length. It has a Jordan-Holder series and it's a finite length. So the length of m mod kernel g is the same as the length of m, but this is only possible if the kernel of g is 0, because you could take a Jordan-Holder series for m and then pull it back here via this isomorphism and get a composition series of length 1 greater by adding kernel g to it. So the only way this can happen is that kernel g equals 0, which implies that g is also injective hence an isomorphism. Okay, so we've completed the proof of Fitting's lemma that if G is an endomorphism of N, then either it is a unit, i.e. it's an isomorphism, or it is nilpotent. So that lemma was the most technical part of the proof of the main theorem, and now we can proceed with the proof of the theorem. So proof of the theorem. Well, we'll take M to be the set of all nilpotent elements in end Rm. i.e. G to the power N is 0 for some N. And we'll show that M is a two-sided ideal. And of course, we know that the complement of M consists of units, and so we'll have proved the theorem. So first we'll show that M is closed under left and right multiplication by elements of end Rm. So suppose M is in M and G is in end Rm. Now since M is in M is nilpotent. So M to the power N equals 0 implies firstly that M is not injective. It also implies that N is not surjective. So it's also not surjective. So that means that if you take G times M, this is not injective. So it's not a unit, but we saw that every element that's not a unit is in M. And this also implies that Mg, the original statement here, is not surjective. Because M is not surjective, so Mg again belongs to M, because the complement of M consists only of units. So M is closed under left and right multiplication by elements of end Rm. Now it only remains to show that the sum of two elements of M is in M. Now to prove that M1, M2 are in M, then M1 plus M2 is in M. We'll prove this by contradiction. Suppose M1 plus M2 is not in M, then it is a unit. So I can find some element M such that M1 plus M2 times M is the identity. For some, well, let's not say M, for some G in end Rm. Okay, and let's call this N1 equals M1G, N2 be M2G. Then because M is closed under left and right multiplication by arbitrary elements of end Rm, this N1 and N2 again belong to M. And moreover, N1 plus N2 is the identity element. So what we have is that N2 equals identity minus N1, and let's say since N2 is in M, N2 is nilpotent, N2 to the power K equals 0 for some K. Okay, so let's say that this also holds. Then what we have is that n2 times 1 plus n n1, no, I want n1 to the power k. Okay, plus n1 plus n1 to the power k minus 1. Well, that's equal to identity here. This is not 1, this is identity of m minus n1 into identity of m plus n1 plus n1 to the power k minus 1. Now when you multiply these two out, the sum will telescope and terms will cancel out, and you'll only be left with identity of m minus n1 to the power k, which is 0. So then what happened? N2 has become a unit, but that's a contradiction because we assume that we know that M2 is in M. So it's nilpotent. And so M1 plus M2 must again be an element of M. And so end Rm is a local ring as required because all non-units form a two-sided ideal.